Hello. Welcome, everybody. Yeah, it must be the new glasses. That's my guess, huh? Where did I go? Who's that guy? Yes, welcome, welcome. Good morning, Fuzzy Yong. Good morning, Uchu. Good morning, Top Wolf. Welcome. Thanks. I don't know how I feel about that one, but I'll take it. Bobby Hill's a good-looking guy, right? Thanks, Chef. Good morning. Good to see you. Good morning, Waffle. Good morning, YCS. Yeah, I might not be. I might not be Mr. P. Might be somebody else. Who knows? Okay, that's going to go there. Hello, Cade. Hello, Kane. It says no shave November. Well, it was for my Halloween costume. I'm not sure I'll go by no shave November. I think I already failed this morning, so no. It was for my Halloween costume, and now I have to rock it for a few months until I get tired of the clean face, and then I'll bring back my facial hair. Fuzzy asks, how's Patty after her altercation? She did get a cut on her foot. I found that. But she seems to be doing okay, so we haven't gone to the vet or anything yet, but I'll keep an eye on her to make sure it doesn't get infected or anything like that. No, I don't think there was another animal in my house. And if there was, it should start smelling pretty soon because it's been almost a week now. Yeah, good morning, Synthos. Rip the stash. No, I'm not doing No Shave November. All right. So it's 11:31. I guess I'll bring back the screen here. We've got a few things to talk about today. Some administrative things. So to begin, let's talk about this. I'm very disorganized. I'm not super disorganized. I'm just too busy to keep track of days. All right, I forget things. Do we have a holiday next week? I think so. Let's go ahead and check that out, shall we? I think Veterans Day is coming up. Someone told me that, and I just want to make sure because we're going to talk about our test. All right? I want to talk about when our test is going to be. Because it's going to be coming up here. So let's go ahead and plan that real quick. We're going to go over recursion today, and that will be the last subject before our next midterm here. So let's pull that up. And let's see. So we're in 2021 here. Thursday, November 11th, Veterans Day. All right. So that means next Thursday there will be no class. That's fine. So for our midterm 2, you guys will have a test on Tuesday, 1 week from today. All right, that's going to be November 9th, I believe. What's on that test? Well, everything that we've covered up until this point. All right, we can check that out just real quick on the syllabus. We're going to be going over, looks like virtual functions. All right, we're going to be going over operators. We're going to be going over templates, which is what we just did. And we're going to cover some recursion. All right. I will post a review before the weekend. So that you have a chance to review that. I also need to make sure I add a practice program for that. I forgot to do that last time. Add practice program. Are there any questions on that? It's going to be very similar to the first one. I will say, Chef, in my previous experience, test 2 usually goes worse than the first test. So here's what I say. You can't expect anything, right? We're going to see how we do. Of course, I make a new test every semester, so it's not like I'm going to be reusing the same one. So I don't know how it will go. My hope is that, you know, it's not worse than the first one. I hope it gets better. But I will curve it if it has to be curved. So that's just my answer to that. If it looks like we're missing out on some stuff, then it will be curved. Are there any other questions about midterm 2? We're going to do that Tuesday, November 9th during class time. Same format as the last test. If there's no more questions, I'll move on here to this bit. I don't know if you are paying attention to Web Campus, but there is assignment 7 out, I believe. All right. This is the templates assignment. Now, it's very pointer heavy. All right. Now, it's not 2D pointer heavy, but it is 1D pointers. This is a dynamic array class. Essentially, you are coding a vectors. All right. You're coding a vector class. You are coding a vector class. All right. Now, in some sense, it will be significantly lower functionality, less functionality than a vector, because that's a library you include with your programs, and that's for math, right? So there's a lot of stuff that's included with that vector class. What we're doing here is you're just going to make your own dynamic array class. My hope is that you can keep this code for yourself, and in the future, if you don't want to import a vector, which likely you just will, but if you want to use your own code, you can go ahead and import your own dynamic array class from CS202. All right. Now, because this assignment is just making a dynamic array class, it's not very exciting, right? Well, to me it's exciting, but for many of you, you're going to miss out on the musical chairs here or the player game. Kind of just like last assignment where you're doing matrices, and this one you're just making a dynamic array class. But I did add a little bit of spice in there. You have an option to kind of do two methods for this. So I am going to post a video for this, but let's just take a few minutes to go over that. The two ways that you can do this dynamic array class. That way, if any of you have some questions, we can get those out of the way right now. So we're going to use Excel for this, just so you can see what's going on. And that's that. So let me go ahead and pull it over here. So, we're going to pretend that these are our dynamic arrays, okay? What is a dynamic array? It's just an array that can hold any number of elements. You're going to be able to insert elements to this array. You're going to be able to put elements kind of in the middle of the array. You're going to be able to put them up front or in the back. All right, so there's 3 total functions that allows you to insert elements to this array. You can kind of see them here in the PDF. I don't want to pick off where I left off, so please go away. I don't know. Okay. So you'll notice here we've got a push back, a push front, and an insert. All right. So the push back puts the element at the back of the array. Push front puts the element at the front of the array. Insert will put an element like I gotta say the word correctly. It will put it at an index in the array. You say, please put this element at index 7, and I'll show you what that looks like. But we'll be inserting it. So everything past index 11 will be shifted to the right. You're kind of just wedging an element into that array. So you've got 3 insert elements or insert element functions. You've also got a delete at function. You'll be able to remove elements from the array. All right. So those are kind of the big ones. We're adding a few additional things in here, such as a sort. You're going to have some operator overloads. Here's some global ones. You've also got some class member ones as well. And then the rest are pretty simple. You're going to sort, you're going to get the size, and that's pretty much it. So the 2 arrays that you can make are, I categorize them as time efficient or as memory efficient. All right, so in a time efficient array, we expect our array to be a little faster than our memory efficient array. Yet our memory efficient array will use less memory than the time efficient array. So both of these have pros and cons. The memory efficient being it doesn't take that much memory, but it will be slower. The time efficient array will take some memory, more memory at least, but it will be much faster. So let's look at these. If you're going to be doing a time efficient array, you're going to need 3 variables. All right, one of them is optional. That's kind of why I pulled this up here to show you. You'll notice I've included an optional variable here. So if you're doing a time efficient array, you will include this optional variable. And what is that optional variable? Well, it is the max size of the array. So your class will contain the pointer, that's the array pointer, which points to the array in memory. It will contain a current size variable, which indicates how many elements are in the array. But you'll also have a max size variable, which tells you how much memory the array has. So there's a difference there between the number of elements in the array and the amount of memory that the array has. So I'll show you what that looks like. Let's assume we've got some elements in here. So in this case, can someone tell me what is the current size of this array? And let's pretend like I've taken some of these off so we don't have to look at them. And what is the max size of this array? Just want to make sure you understand that we're clear on what's going on here. So the current size looks like it's 8. Yeah, there's 8 elements in here. And what's the max size? It's 11, right? So yeah, so I see that we're kind of understanding that, right? Now, the idea here is that this array has some empty space. And how does that benefit us? Well, if we're doing an insert function like insert pushback or push front, depending on the size of the array, like the max size, we may not have to request more memory from the operating system. In fact, we might just be able to plop it in here. So if you're going to do a pushback, as long as you have space, you can say, hey, I'll put my new element here. Let's say my new element's a -1. I just put it in there. Just like that. Snap of the finger, it's in there, that's fast, right? Similarly, let's say I do a push front. All right, that means I want to put something up front here. There's 2 things I have to do. For one, I have to shift everything over. And then I'll put my new element up front. Now, that is still faster than requesting more memory from the operating system. All right, when you request memory from the OS, you have to wait for it. It's like you're talking to somebody. But when it comes to just shifting elements, you can go ahead and get to work right away. You know that memory is yours. I'm just going to get to work on it. So that will still be faster. And then lastly, if you're going to do an insert, let's assume we'll do an insert at index 0, 1, 2, 3, 4. All right, that's index 4 right there. If I'm going to insert an element at index 4, I need to shift every element greater than or equal to index 4 to the right. And then I will put my new element in here. So those are your three functions. Now guess what? At this point, you've run out of memory. So you didn't escape requesting more memory from the operating system. Now, if we're going to request more memory from the OS at this point, do you think we should just request an array of size 1 bigger? Or do you think we could be a little more efficient with that? If this is a time-efficient array, do you think how many spaces should we request? What do you think would be reasonable? That's a good question, Kate. I'll get to that. But I'm just curious here. It looks like this array... Yeah, Chef says maybe 11 more. I think that's a reasonable number. All right, even in your program, you could request maybe 100 if you wanted to. I would say that's pretty okay. All right, so in the case that you do run out of memory, you can tack on a whole bunch. You know, just bring them over here and say, all right, I've got all these new spaces. All right, and now for the next 11 inserts, you will not have to do any kind of memory stuff, right? You're not going to have to request more, deep copy, resize, all that stuff. Now, delete at is a very simple function in this one, okay? Delete at is a very simple function. What do? Say I'm deleting at index 4, I just remove it, and I shift everything over. Now, clear array. Clear array is supposed to empty the entire array. Okay, Chef, that's a great question. Let's just answer that real quick. Just to be clear, you are not allowed to do that. I kind of skipped some steps here. All right, if you're going to do that, Chef, if you want to add memory to an array that's already been created, you can't. So what do you have to do? You have to kind of come down here, make like a new array. And you say this new array is equal to the old size, say, plus 11. And then the next thing you have to do is copy in all of these elements, right? I was just kind of shorthanding it, that's all. You'll have to copy in all of the elements. And then what do you have to do? Well, you have to delete this array. You say, I don't want it anymore. Have it back. And then you have to say, array, you are now pointing at this one. Does that make sense? Yeah. I was shorthanding it, that's all. Yeah, obviously you're going to have to request more memory. Okay? You're going to have to request more memory. But the point I'm making here is that request a lot of memory. You know what I mean? Yeah, you still, let's see. I got a bit lost here. Yeah, Pig, you're right. We just allocate more memory. Synthos, yeah, we have deep copy it. And then Cade. Well, so we'll talk about that in just a moment. I'll answer your two questions. Let's kind of start with that one here. The array is considered dynamic because it will have the ability to be resized. Now, an array that's allocated into a pointer does not have that ability. But the code that we are writing is essentially making a dynamic array. Obviously, this pointer is not dynamic, but we can kind of move pointers in and out. You know, we can say, all right, this pointer is now pointing to some different memory. And that's kind of what makes it dynamic. Pig, assuming I understand the question properly, in the sense that if we're still talking about just being able to tack on memory, Well, it's okay. I'm going to answer this anyway. Why can't we tack on memory? Like to say, here, I've already got this array. Why can't I just add some more onto it? Well, your operating system is always monitoring all of the memory that's in here. And so your brother logs in and says, I'm going to be doing Minecraft. So I need some space for my iron pickaxe. So that belongs to Minecraft. And then you log in and you say, I'm writing a program for this class. And so this needs some memory for that program, whatever it might be. Maybe it comes down in here. And then someone else logs in and says, hey, I actually need an array. And this array is contiguous in that the elements are side by side. So the block has to be a minimum size. That's to say, I need at least a block of memory that's, say, I don't know, what's that? That 9 bytes about? Let's say I need it to be 15 bytes in contiguous length. 15 bytes in contiguous length. Well, if we check here, this is not 15 bytes in contiguous length. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's 1 too short. So in fact, the block has to come down here, and it's going to then take these 15 blocks of contiguous length. That is, of that it can fit. It looks like I did my math a little bit wrong there, but yeah. So now you say, I want to tack on more memory to this array. I want to tack on 16. Well, who's to say that there's someone not taking memory here? Let's say program GG is taking this memory. And so you can't just tack on to this array. Am I making any sense here? I now need 16 more blocks. So we're going to need 15 plus 16 more blocks for a total of 31 contiguous spots in memory. 31 contiguous spots in memory. No, you do not want to illegally access. And so based off this, if this is how memory is looking, there is no room here to get 15 contiguous, or 16 more. Here we have 15 contiguous spots. And then we say, let's see, can I just tack on some more? 1, 2, 3, 4, 5. That's 15. And then boom, I'm stuck. Program GG is taking up the 16th spot. So I can't do that. So instead, I have to go somewhere else in memory. And I have to say, hey, operating system, will you do me a favor? Will you find me 31 contiguous spots in memory? And if it does that, then you'll see that that's kind of why we have to. That's why we always have to request new memory. We're not allowed to just tack stuff on, because the memory has to be contiguous, and we can't expect the operating system to always have that contiguous memory for us. All right. Pig says the memory has already been used for something else, so you can't just allocate. Yeah, what I'm saying here is there's no room. There's no more room. Let's say your sister logs into Club Penguin or something. I'm assuming you have a family server for some reason. None of you have local machines. You just have a family server. And the operating system says, hey, your sister gets this memory for Club Penguin. And you're saying, all right, I need 5 more spots for my array. The operating system says, well, I can't give you these spots because I've already given them away. So what you'll have to do is request some different memory. And then the operating system will go find some nice open memory for you and give it to you. So am I clear on that? Does it make sense why you can't just add spots to an array? Pretty much every time we have to resize an array, we have to get a whole new memory address. Is that clear why? So Synthos, no. I mean, that's kind of a vague question. When it comes to an array that's being stored in a single pointer, yes, it has to be contiguous. When it comes to a two-dimensional array. Do you remember that? Do you remember the two-dimensional array? Let's go look at that. This one's pretty good. That was last class, wasn't it? Do you remember this thing? Tell me, what do you think? Is this entirely contiguous? Is the whole matrix itself contiguous? No, it's not. But portions of it are contiguous. Okay, portions of it are contiguous. So it's all dependent on the pointer that you're working with. The mat is a double pointer. So this memory here will be contiguous. And then each of these addresses will be pointing to something else that's contiguous. In the sense, if you're just working with a single pointer, it must be contiguous. If you have a single pointer, like you do in this assignment, it has to be contiguous. Now next, in a few weeks, I mean, we don't have much time left, but we will talk about linked lists. And linked lists are a way of making an array that's not contiguous. So we'll talk about that later. So now that we're kind of back on track here, hopefully you understand how the time efficient array works. Now in a memory efficient array, let's say I want to add something to this. If I want to add something to it, I have to make a new array every time. Every single time. I'm going to say it has to be one bigger. I'm going to copy everything in. Right? I'm going to add whatever element I want. I'm going to delete the old one. And then I'm going to say, hey, the new array, you are now looking at this array. If I'm going to delete an element, right, I have to request memory from RAM that's smaller. I'm then going to copy everything over except for the one I'm deleting. I'm then going to delete the old one, right? And then I'm going to say that the array is now looking at the new array. So in a memory efficient array, you will never have more memory than you need. So you don't need that optional variable max size. You just need the current size. Because the current size is describing how many elements there are and exactly how much memory space you have. Fuzzy, yes, it is a popular interview question. You will probably have it on your test. Memory I'm referring to is RAM. Okay, it does seem like a pain, but you have to do it in both cases. In this one, you'll just do it less, but you still have to write the code to do it. Okay? So that's that. Now, I'm going to come up here back to Cade's question in which they said, when would you use time versus memory efficient? Well, suggesting you have a little firmware chip that has 2 bytes of, not 2 bytes, say it has 100 kilobytes of memory on it. 100 kilobyte piece of RAM, you probably use memory efficient there because you don't want to take any more than you have to. Say you're working on my machine here. My machine has, I think, 16 gigs of RAM. That's pretty good, right? Some servers have hundreds of gigabytes of RAM. And so if you're going to hold up, an extra 100 bytes of memory, I think it's not a big deal. So it all depends on how much RAM you have, and if speed is something that you care about, then absolutely. If speed is something that you don't care about, then memory efficient is a good way to go. So are we all clear on this? I will be uploading a video. You can watch it, but I just want you to know the difference between these two, and you're welcome to do either one. Now I'll make you aware. There is a little shortcut you can take, and if I see you take the shortcut, I'll find you, and I will deduct you points. In this assignment, if you are doing a time-efficient approach, do not allocate an initial array of size 10,000 plus. Why? Well, because my testing program will only test with about that many elements. And if you allocate an array that's bigger than that, your program will never get to a part where it has to resize the array. I have to confirm that you know how to do that. So you have to make sure that your initial array is smaller than this. So that at least one point in time, you have to resize the array. I will go through your code, and if I catch anybody doing this, I'll deduct at least 30 points, 30%, and that's because that's your memory points. You get 30% for correct memory operations, and if you skip over them, then I will not give you those points. So be clear on that, okay? You can take the shortcut, and you could get 70% if you wanted to, but please do not do this. Ask me questions. Let me help you resize the array, okay? Don't just skip over it. Do not take this shortcut. Hopefully I'm clear about that. So that is the assignment. All right, any further questions? Because if not, we're going to move on to the fun stuff for today. How we copy the address of a new array into array? Well, in your class, you have, I don't know, maybe you have void insert here. Type T. I don't like that. And you say, all right, let's say this is memory efficient approach. It could be either, honestly. So what do I need? Well, I'm going to need a type pointer. New array is equal to new type, right? Say something +1. Something like that. And then in here, you'll do a deep copy from array to new array. Okay? And then you will insert the element to new array. And then you say, I don't need the old array anymore, so I delete the old array, and then I copy the address of the new array into the old array. And then if you're picky about aliases, you say new array is equal to null pointer. That's it. So, Chef, you don't want to deallocate the new array because we're working with an address here. If you deallocate the new array, then you'll be deallocating the new array. You only need to delete the old one, right? In the original, I don't know, we kind of did this thing here. Let's say this was the old array up here, and we're inserting some element, say 8. If we're going to put an 8 here, we need to then get a bigger array, right? And the new array will be looking at this one. Now, which of these do we care about now? That we've inserted an 8 here, which one do we care about? Well, we care about this block of memory. This block of memory no longer has any use to us, so we delete it, right? And then you say array equals new array. Yeah. We had a moment. Please tell me when you're back, please. I'm going to take a moment for myself. All right, thank you. So the question is, which one do we care about? Obviously, it's this one. So then we just overwrite the old array with the new array address. And then what happens if I delete new array? What if I do that? Well, I'm now deleting this memory, right? And now I've deleted all of that nice work that I did. So, Chef, does that answer your question? No, you don't delete the new array. You're simply going to just move one address from another, right? You definitely don't want to delete the new one because then you'll be deleting the one you just requested, basically. All right, so that's some pseudocode for you. You're welcome. I don't know, maybe increase size here. Ooh. Fancy. All right, everybody. Now let's talk about our subject for today. Recursion. Hope you're excited. I hope you're as excited as I am, because recursion is something fun. Now, the first thing I'm going to do is tell you that, congratulations. We have made it past all of the C++ stuff, except exception handling, which I'll see if we have some time for. What does that mean? Well, there's no new C++ stuff to learn, at least from this class. There's some additional things, right, that you might talk about. That's exception handling, as I just mentioned. Enumerators are something that you might look at. And then anything greater, any C++ version greater than 11. There's some more stuff. But in this class, we're officially done. All right, I'm saying maybe on this one, but we're kind of officially done with learning C++ things. All right, we learned about the pointer. We learned about classes. We've learned about inheritance, operator overloading, templates, all of these things, virtuals. And now we pretty much know 90% of how C++ works. So for the rest of the semester, you are now entering more the world of computer science, all right? We are stepping into the science part of CS, all right? So I hope you're excited. Kind of from here on out, except for CS 218, your future classes will be more based on computer science, kind of theoretical concepts, and less about how do we code this program. Does that make sense? You're going to talk about data structures. That's not a hardware thing. That's not a programming thing. That's something that computer scientists have come up with. So, kind of for the rest of this semester, we're going to talk about kind of some theoretical things. So, kind of academic. You're kind of graduating here a little bit. It's a proud moment for you. All right, and you are lucky enough to start out with recursion. All right, you're lucky enough to start out with recursion. So, let's take some notes here. There's not a whole lot of notes on recursion, but we will be taking quite a lot of examples to get to know what's going on. Uchu, definitely not less programming assignments. So for example, this assignment you're working on now is to build a dynamic array class that uses templates, in which you're practicing using a template, which is a C++ thing. Your next assignment, you're going to be practicing using recursion. Recursion is a computer science thing, all right? Templates, C++ templates are specifically C++. Recursion is a universal computer science concept. So no, you won't have less programming assignments. If not, you might have more in the future. But it's going to be less geared toward practicing C++ and more geared toward being a scientist, all right? So I hope you're excited. I know I am. So let's start with the basic definition of recursion. I know some of you have heard it before. Does anyone know? Does anyone have any ideas? You're allowed to speak up if you'd like. I'm going to show you the funny joke that Google does with recursion. So I ask you, does anyone know what recursion is? Or does anyone know anything that is recursive? Fuzzy, kinda. To me, it sounds like you just described a loop, but you're not far off. All right? You're not far off. Now, check this out. What did you just see here? If Fuzzy, you probably did post a meme about it. What is recursion? Fibonacci. Yeah, Brandon knows. The Fibonacci sequence is the first thing that we'll talk about that's kind of recursive. Now, Google has a funny joke here. Let's see how funny Google is. Did you mean... So, notice I spelled it right. And I can just endlessly click on this. Wow, Google, you are so funny, right? Isn't Google hilarious? Well, I'll talk about what this means in just a moment. But in some sense, this search for recursion is recursive. That I can just endlessly click on this and it takes me back. Wow, Google, you are hilarious. Thank you for that. So, what is the definition of recursion? Or the definition of a recursive function, rather. It is a function that is defined in terms of itself. All right? It is a function that is defined in terms of itself. Now, we'll talk about what that means in a moment. But many of you are talking about loops. So I want to bring it out. I kind of want to bring it to light because many of you are correct. All right? Right now, we think in terms of iteration. This is how you've learned stuff. That's loops. Iteration is loops. That's repeating something over and over again. Something that is recursive, kind of by definition, it is itself in some weird way. Synthos, you'll see. So real quickly, I want to talk about Alan Turing. All right, now this is not a CS history class, but I do want you to know. If you don't know who Alan Turing is, he's kind of the father of computer science. If you would like to see a modern day movie about Alan Turing, you can watch The Imitation Game. And he's played by Benedict Cumberbatch. And The Imitation Game is about World War II, in which the Germans were encrypting their communication with something called Enigma. All right? And Alan Turing is said to have ended World War II at least 2 or 3 years earlier than it would have, because Alan Turing first built a computer. He built one of the first computers that automatically cracked Enigma codes. So that's kind of a proud moment for all computer scientists. The father of computer science was responsible for ending World War II, many say. I guess historical interpretation is up to that, but I do believe it's very true. So if you're interested, I would recommend watching that movie. I think it's a good one. All right. So what he did was he first created a machine to crack Enigma. He was also an academic. There's many papers that he's published. And what Alan Turing did, namely, that's related to recursion, is he proved that anything that uses a loop can also solve the same problem with recursion. So I don't know if we have, he was British, yes. And if you want to know a little bit of fact about him, I like talking about Alan Turing. He was homosexual, which was illegal at the time. And so he had a very sad fate in which he was prosecuted for being homosexual. And they had Great Britain had two ways of dealing with that. One was, I don't remember what one was. I think he had to go to jail or something. But the other one was he could take these pills that would essentially castrate him, basically remove all feelings he had for other people. But little did they know back in the day those pills were toxic, and they ultimately ended up killing him. So I was really sad. And then later, not very many years ago, I think in 2000s, obviously homosexuality is no longer a crime. And I think I don't know, the Queen of England or whoever does that, they knighted him. So Alan Turing, after he died, was knighted. And he's a knight in England or Great Britain, which I think is pretty cool. And obviously they didn't make up for what they did, but to some sense they did. Yes, he is the guy that made the Turing test. I'm not a biology person on that. I'm not going to talk about that, Uchu. I'm sorry. I'll let you do your own research on that. I just knew that the pills were toxic. They were obviously destroying his body. So, Alan Turing, a knight, proved anything that uses a loop can also solve the same problem with recursion. Now, that kind of, no, that will not be on the exam. Not on the exam. I'm just giving you some history, that's all. I'm just giving you some history. I want you to be excited about recursion, so I want to tell you about it, that's all. So what does that mean? Well, recursion is kind of just a different way of thinking. Recursion is kind of a different way of thinking. Meaning recursion and iteration is kind of the same. It might even be the same. It's just looked at from a different perspective. So I'll let you think about that how you will. I'll also kind of excite you. Quantum computers, I know that many of you might know that quantum computers are kind of becoming a real thing. And if you want to code for a quantum computer, it's best done recursively. I don't even know if they have such thing as a loop on a quantum computer. Recursion is the way. All right. So just some fun facts. Not on the exam. Just some fun facts. Now, there are programming languages that only use recursion, meaning that there's no loops. So, you will have to code in a language that does not have loops. Usually these are called functional programming languages. Functional programming languages, if it's purely functional, doesn't even have variables. You can't even define a variable. Everything is just represented as a string of functions. And it's quite disgusting. It might look something like operator equal, and then you pass in A and B, but B will happen to be an operator plus B and C, but C might happen to be an operator minus of C and A, stuff like that. So it kind of just builds out to be this big, disgusting functional thing. But functional programming languages often are recursive only, meaning no loops. So you have to learn this, all right? You can't get out of it. So pay attention. All right? Some of those you'll see is Lisp, Scheme. All right? Those are purely functional languages. You might think that, but I'll let you reevaluate that in the future. Haskell. I think I did that right. I'll let you evaluate that in the future. It's not that limiting. Like I said, recursion and loops are the same thing. And these programming languages have implemented some things to make it easier on you. But I will let you know, I've coded some programs before that are unreadable. So when are you going to learn about this? Well, you'll probably take CS326 at one point. That's the programming languages class. And that's probably the most prominent one in which you'll use some of those languages. But recursion will especially come up in your CS477 class. That's the algorithms course. And in many other courses, you will learn about recursion. CS302 even. All right, so be prepared for that. So let's get into some recursive stuff. Pig asks, what makes a computer quantum? It's a bit. Our computers work in a series of zeros and ones. All right. So it's either 0 or it's either 1. In a quantum computer, it's not a bit, but it's a range. It's a range. It's like a percentage. It's like the likelihood of something that will happen. So each bit is a range between 0 and 1. All right. In our computers, it's just a bit. It's either 0 or it's 1. In a quantum computer, it's a range. It's a 0.33 or something. I don't understand very well, but it's pretty new. You think makes you happy to be a CPE major? Perhaps. I was a CPE major, but I switched to the computer science life personally. It all depends on who you are. You're going to know plenty of coding in your major anyway. All right, so the first thing we want to talk about is recursion is memory intensive. Memory intensive. What does that mean? Well, it uses a ton of memory. All right. Loops use less memory in general. All right, so that looks like a pro or a looks like a pro and a con right there, right? Pro and a con. It looks like recursion's already losing right off the bat. So you're going to ask this question. If recursion uses a lot of memory, why not just use a loop? Well, I think there's really one main reason for this. All right, there's one main reason for this. And there are some functions or problems that cannot be very easily solved with the loop. And on Thursday, we will go over one of those problems. All right, so there are many problems that are very hard to solve with a loop, in that you need lots of specific cases. Recursive solutions are often, it's like art. All right, you might not think this, but oftentimes if I write a recursive function, I feel proud of myself. I kind of want to put it on the fridge. Recursive solutions are often elegant. Simple, and general. Back to that word that I talk about, general. They're often very general. Some problems, if you're going to use a loop, you're going to need all these specific cases. Your code will be a million lines long, but the recursive solution comes out to be maybe 20 lines of code. So Uchu asks, recursion doesn't really have any formulas. Well, I'm going to see if I can understand your question properly. I'm going to try to answer it like this. And many of you will not be happy to hear this. But there is not a super easy cut and dry. Did I say that right? Cut and dry way to convert a loop to recursion. All right, there's not a super easy way to do that. So I don't know if that's what you're asking, but no, you can't just kind of look at a loop and be like, I'll just put it in my black box and I'll get out a recursive solution. It doesn't really work that way always. All right. The way to do this is you must think recursively. All right. You must think recursively. You must think recursively. And how do you do that? Well, the first thing you need to start with is break the problem into kind of some building blocks is what we call them, into the simplest of cases. Break it into a bunch of smaller problems. Break the problem into smaller problems. As you do that, you're going to identify what we call a base case. What is a base case? Well, that's where our recursion stops. All right, that's where our recursion stops. So once you break the problem into smaller problems and you identify your base case, then you're going to be able to kind of code your problem. All right. So let's kind of just talk about all the things we need for a recursive function. All right. And we're going to get to some coding today. Obviously not so much code today, but we will have a little bit. So hang in there with me, please. So a working and valid, keywords here, a working and valid recursive function always has three things. The first thing it needs is the very definition of what makes it recursive, and that is a function call to itself. I think we're okay. Am I still alive? I think I'm okay. The second thing it needs is a base case. All right, let's kind of define these as we go. All right, a function called to itself. I spelled that wrong, didn't I? Function called to itself. That makes the function recursive. A base case. This is what stops the recursion. This is what stops the recursion. It says, all right, you can stop. You don't have to continue on anymore. We've solved our problem. And the third thing you need is a reduction operation. Now, a reduction operation takes the function one step closer to the base case. All right. So right now, you don't know what I'm talking about. Okay? That's fine. You don't know what I'm talking about just yet. But we will define this, and you're going to be able to kind of piece it together. All right? Just remember, this is a question I will ask you on the test. That is, what three things do working, valid, recursive functions have? They have a function called to itself. That's what makes the function recursive. That's what makes the function recursive by definition, right? Where did I define it? Up here. It is a function that's defined in terms of itself, i.e., it calls itself. The second thing it has is a base case, which tells it now you can stop. Okay, you can stop calling yourself. That's what it says. Stop calling yourself. My dad used to take a pool noodle and he would like turn it around and whack me on the head with it, and he'd say, "Stop hitting yourself." It was funny. It wasn't abusive, I swear. I'm just saying. It's similar. You can say, "Stop calling yourself. Stop calling yourself." That's what the base case is. And the reduction operation takes the function one step closer to the base case. Pig, I appreciate it. Yes, recursion is, in my opinion, one of the coolest things about being a computer scientist. Try talking to your friends about this. All right. So for now, we're going to stop with the notes. Let's go ahead and bring out some examples and some code. I am going to pull up Google Chrome. Let's cross our fingers that the RAM does not get hogged. Yeah. Oh, man. I was just thinking about it that way, that's all. I was thinking, stop calling yourself, stop calling yourself. That reminds me of my dad. My dad was just playing with me, that's all. He was a pool noodle, right? He's just whacking me. Okay, so the first thing we're going to look at is the Fibonacci sequence. And I just want you to put it in terms of a mathematical definition. Sounds like a villain origin story. Yeah, perhaps. The real reason Mr. P became a computer science instructor. Okay. All right, here we are. Let's go to Wikipedia, shall we? All right. Here we are. The Fibonacci number. All right, it's a sequence of numbers. All right, and so in some sense, we can define a function to give us the nth Fibonacci number. Produce the nth, I'll put a dash here, fib, I'm going to say fib number because that's a big, I could try, Fibonacci, I think I did it. Produce the nth Fibonacci number. So it's an integer. It is an unsigned integer. You see I do this a lot. It's an unsigned integer. It's not negative. All right, and we're going to call it fib. And it will take the nth Fibonacci number. So that's kind of like our function. Okay? Now, what does this mean to be recursive? Well, it's defined in terms of itself. So let's go ahead and look at this. Notice here, I'm going to just kind of snipping tool and close out of Chrome because I'm scared of what might happen. Okay, here we are. So this is our function. This is our function. Do you see that it's defined in terms of itself? If we were to put this in kind of code, what would this look like? This would look like this. You would say that, say, fib of n is equal to fib of n minus 1 plus fib at n minus 2. So hopefully you're seeing this here. I've made it a C++ function, right? And I'm kind of converting it here for you. Now, what part of this makes it recursive? Well, I'll give that part to you. What part of this makes it recursive? It's this. Notice the F there and the F there. That means that it's contained, excuse me, I didn't really hide myself all too well there. I'm sorry if you saw. I'm a little sick right now. I had to do some gross person stuff. I'm sorry about that. I meant to hide my webcam, not my computer screen. Anyway, back to what we're talking about. What makes this recursive? Well, this is kind of like our body, right? So if I were to make some crappy curly brackets here, whoop, there you go. That's like our C++ function. And contained inside of that body are function calls to itself. So what makes Fibonacci recursive? It's that we've got these F's in here. All right, you're calling yourself here. That's recursive, that's recursive. Now, what's next? Can anyone, just thinking about it, can anyone identify what might be the base case? Now, I haven't really given you a great definition of what that is, but a base case is something that stops the recursion. Does anyone see anything in here that might be a base case? Does anyone have any ideas? Yes, Chef, that's exactly right. That's exactly right. Notice here that we've identified kind of these two cases here. When n is equal to 0 and when n is equal to 1. When n is equal to 0 and when n is equal to 1. We're going to say, hey, you're not defined recursively anymore. You can just return 0 here. In this case, you can just return 1. Okay? So this here is our base case. All right? Very good, very good. This is our base case. Boop. Here's my terrible... I don't think it looks terrible, but it's all right. And then, how about the reduction operation? So Cade asks, the base case could be the start of the conversion. I'm going to swap your head around here. It's the end of the recursion. It's the end. It's when it stops. Now I'll show you. You're thinking about it correctly. You're going to have to see it in action. Okay, you're going to have to see it in action. Obviously, 0 and 1 look like the start of something, but a base case just kind of tells us when something ends. And you're going to have to see it in action. Now, can anyone identify what the reduction operator is? Is there anything here that takes us close closer to our base case. We've identified the recursive component. That's here. That's the F. The recursive component is the F. The base case is up here. F of 0 is 0, and F of 1 is 1. What's the reduction operation? What is it taking? What's taking us closer to the base case? That's absolutely right. Yes. So when you give the function an n, it works backwards. That's exactly right. I'm so proud. It's working backwards to find n minus 1 and n minus 2 until it reaches a base case. And then it will fold back up kind of like a ladder. And we're going to do plenty of Microsoft Paint visuals. When we get to recursion, we're going to start making some visuals here. So there's our reduction operation. N minus 1 and n minus 2. Nice job. Okay, we've identified them. Is anyone lost? I'm sure some of us are, but this should make sense, hopefully. We've got our base case, we've got our recursive part, our recursive component, and we have a reduction operation to take us one step closer to our base case. So the sequence goes like this, right? It basically says you have the first two numbers are the base case, 0 and 1, right? That's where it starts. And if we're going to say n is equal to something, that's the 0th number, right? And that is the, whoops. And that's the 1th number, right? I'll put some lines down here. Now, number 2, Fibonacci of 2 is equal to, right, if you want to fill this in, fib of 2 minus 1, which is 1, and fib of 2 minus 2, which is 0, which happens to be 0 and 1. So 0 plus 1 comes out as 1. So now, can you help me continue on here? Let's say fib of 3. Fib of 3 is equal to fib of 2 plus fib of 1. What does that come out as? Are you sure? It's not 2 plus 1. It's fib of 2 plus fib of 1. This is fib here, by the way. This is the fib. All right? This is n down here. It comes out as 2. You take 1 plus 1 is equal to 2. 1 plus 1 is equal to 2. So for those of you who missed kind of what's going on here, this is just the n. This is just what's being passed to the function. Up here is what it returns. So does that make sense? So the next one comes out as 3. That's 1 plus 2 is 3. The next one is 5. Why? Because 2 plus 3 is 5. And then the next one is 8. Why? Because 3 plus 5 is 8. Finally, this one comes out as 13 because 5 plus 8 is 13. So when I say, what is the 7th Fibonacci number, or the nth Fibonacci number, maybe not 7, but it'll say it's 13. Because what? N equals 7, it will happen to be 13. What's the 0th Fibonacci number? That's 0. So are we following so far? So let's make some code here. Here we are in the function. First, we need the base case. I'm just going to kind of speed through this. If n equals 0 or n equals 1, return n. All right, this just returns 0 or 1. Okay? If n equals 0 or n equals 1, we'll just return it, right? Because the nth Fibonacci, if it's 0, is 0, and if it's 1, it's 1. So that's our base case. Next, we need a recursive call to itself. So we don't need an if-else here because there's a return in this statement, and Clang Tidy will be mad at us. But here's where we do this part. Now, we don't need this equals part, right? Because that's what we're returning. And this will be equal to n minus 1. This will be n minus 2. And that is the function. That's it. Now, the reduction operator is in here, right? So the recursive call is you're calling fib again to fib, right? And then the reduction operation is -1 or -2. Are you with me so far? That's it. That's all. That's all. Now, I'll let you run this on your own. Next class will come back, but I do want to take a moment to show you what this might look like on a paint diagram. I just want you to think about it. So you could go to bed tonight and have dreams about recursion. And then when I see you next class, you're going to have a better idea of what's going on here. So let's bring out Microsoft Paint for the last, 8 minutes of class here or so. Your dreams will be recursion. All right? And so up here, we're just going to put it in your head, okay? It won't be a nightmare. We're just going to put it in your head. So I'm going to use this kind of off to the side here. So we'll just save that. So let's say we're going to do the Fibonacci number of, let's start very simply. Let's do 3. Do I want to do 3? Yeah. Fib of 3. What is that equal to? What is fib of 3 equal to? All right. Well, fib of 3 ends up calling itself. Do you wake up at the base? So Inception. Have you ever seen that movie, Inception? That's recursion. Just so you know. If you've ever seen Inception, that's kind of a recursive paradigm. I don't know the proper way to say it. But it is a recursive idea. That's what Inception is, kind of by definition. Yeah, a dream. The dream itself is a dream. Whoa, crazy, right? And what's the base case? I don't know. The sleeping person, something like that. The kick. Maybe the kick is the base case. So that calls fib 2, fib 1. Let's do it the other way, just so I have some room. That's fine. These are a little bit too wide. But I think it's good. So, check it out, guys. Fib of 3. What is that equal to? Well, you know that that's equal to fib n-1 plus fib of n-2. Right? So, in some sense, we're going to kind of put it down here in which it calls this. So it calls itself, right? There's this little line here indicating that I'm calling myself. And here I'm calling myself. And here I'm going to put a little plus sign. Plus. Okay. Now what does this come out as? Well, you know that this one is going to be fib of 2. Right? And you know this one's going to be fib of 1. Now, similarly, this happens, right? The same thing will happen on fib of 2. It's down here. But what happens here, right? This one, you know what this one does. That one just is going to return 1. So I'm going to go ahead and kind of put a little dinky thing out here. We'll just say that's 1. We reached the base case. We're not going to go any deeper into our dream. But this one ends up calling itself again, right? This one calls itself again. So now we're down here. And we're down here. And what do you know? We're kind of at the bottom now, aren't we? So what does this come out to be? This comes out to be fib of 1. Do you guys see what's happening here? And Cade, I'm curious, does this help answer your question about starting and ending? Starting and ending. Now, what do these things return? Well, we know that this one just returns 1. And this one returns 0. And up here, you've got a little plus sign. Use a little plus sign. So, what does fib 3 do? Well, let's get out my kind of highlighter here. Fib 3, what does it do? It says I'm going to call fib of 2 and fib of 1. So I call fib of 2. What is fib of 2 going to do? I'm going to call fib of 1 and fib of 0. Comes down here. What is fib of 1? I'm 1. What is fib of 0? I'm 0. So what's 1 plus 0? Well, that comes back up to 1. Right? Comes up to 1. And then this is not done yet. Now we have to come over here. What is fib of 1? Well, it's just 1. So that comes up here. What's 1 plus 1? That comes out to be 2. So what's the third Fibonacci sequence number? It's 2. And these are all the base cases down here. Let's identify those. These are our base cases. That's a base case there. That's the base case. Notice the recursion stops here. It doesn't go any deeper. It stops. It says, I'm done. Okay. The reduction operation is happening here. Give it a little star. I feel like I'm in grade school. Whoop. Here's your reduction operation. All right. Reduction operation. There it is. And then the recursive call is the fib. So the reduction operation is the n minus 2. I've made a grave mistake here. Okay? It's the n minus 1. That's what reduces. That's what's reducing it. So I'll take some time to kind of pop that out. But since we've got some time, let's pull up MOBA just real quick. I want to show you something fun. But we're pretty much done with class for today. If you want to see me run this program, just hang out for one moment, please. Now, didn't I say this is memory intensive? I did. So, prepare yourselves, folks, because we are about to see something fun. Yeah, you're right. It is sick. I'll show you its purpose soon. All right, next time we'll get into its purpose. I'm going to show you a problem that you can't solve with a loop. I mean, you can. If you do, I'll give you extra credit, but good luck. That's all. That's all I'll say. Good luck to you. We'll do that next time. All right, you ready? Say goodbye to Bobby, folks. Wow, we didn't make it very far at all. So we printed this one. We printed that one. That's 55. It's still working on this one. It's still working on this one. It's still working on it. Why? Well, look at this paint diagram. Think about how wide this gets. This becomes very, very wide. It's got a fat butt pretty much, right? It's like way super wide. So what happens here is I'm doing a function call to itself over and over again, and then we're piling on RAM. We're piling on more RAM each and every time. So this might return sometime, but I guarantee you this will take, I don't know, I'll estimate a year. This one will take, I don't know, 10 years. By that time, Bobby will run out of memory. Cool? So that's all I have for you today. Thank you for listening to me. I hope you think you've got an idea of what recursion does. Next class, we'll get into the better details of it, right? So obviously, we won't have we'll have some goofy examples still, but nothing terrible. And dream about recursion. Come back next time ready to learn. I appreciate you all coming to class today, listening to me. Get started on the assignment. I'm here to help you. Come to office hours if you would like. But that's all I have for you. Synthos, hang out for 1 second, actually. I don't know what CPU Bobby has. So Synthos, if you look up the quantum computer that Google AI ran, the problem they solved was estimated to take, I think, it might have been, I think it was 11 years. And I think they solved it in 40 seconds. Okay? So, yes, there are computer science problems that will run until the sun explodes. Absolutely. You'll learn more about that later. Cade, you're welcome. Have a great day. Young, you're welcome. Kane, you are welcome. Nick, have a great day. Cade, the assignment 7 is due. I think I made it Saturday. Saturday or Sunday, one of those. You can take a peek on Web Campus. Fuzzy, you have a great day. You are very welcome, and I will hydrate. Chef, have a good day. Giovanni, have a great day. You're welcome. Synthos, you're welcome. CS2 student, you are welcome. Yeah, it is crazy. It's due on Sunday, it looks like. Thanks for checking that out. Cade, have a great day. Uchu, have a great day. And Top Wolf, have a great day. Good to see you guys. I will see you next time.